We can start the lecture now. On Friday, that's 23rd of October, I made 3 recordings, which cover all of chapter 2. So I suggest you listen to these recordings to review chapter 2. Today we are going to start with chapter 3, which is on derivatives. Okay, tangent lines and the derivative at a point we are going to define right now. You know what tangent line is. This is the definition of the slope of a curve. Y is equal to f of x at a particular point. That's x sub 0 and f of x sub 0. X sub 0 and y sub 0, you can say that too, because y is equal to f of x sub 0. Okay, is this limit? So the slope of the curve is f of x sub 0 plus h minus f of x sub 0 divided h, and you take the limit as h goes to 0 from both sides. Now, if this limit exists, this gives us the slope of the tangent line. And it's also called the slope of the curve at that particular point. So let's continue. Now let's just keep this definition in mind, because that's the basic definition, mathematical definition of the slope of the curve and tangent line. Okay, so what we do is basically, in order to calculate the slope of the curve, we calculate f of x sub 0 plus h and find this limit. Y sub 0 is f of x sub 0 here, as h goes to infinity, as h goes to 0, sorry. Now the line which passes through this point and which is tangent to the curve can be written like this. Y is equal to y sub 0 plus mx minus x sub 0. M is the value of this limit. If this limit does not exist at this point, then you don't say that that's the slope of the curve. Okay, so if you want to make an example, suppose y is equal to x squared, and x sub 0, y sub 0 is 2, 4. Okay, so I calculate the limit as h goes to 0 of 2 plus h squared, which is f of x sub 0 plus h, minus x sub 0 square, of course, square of 2, which is equal to 4. Now, if you open this up, 4's cancel out, and h cancel out here, you are left with 4 plus h, and as h goes to 0, the result is 4. So, therefore, the tangent line at this point, at 2, 4, by point slope formula, 4 plus 4 times x minus 2. That's called the point slope formula, because y, if you take 4 to this side and divide by x minus 2, that gives you the slope of the tangent line. Okay, let's look at it pictorially. What happens here? That's your function is the blue, y is equal to f of x. That's the point x sub 0, f of x sub 0. That's the point x sub 0 plus h plus f of x and f of x sub 0 plus h. So the coordinates of q is x sub 0 plus h and f of x sub 0 plus h. Now, if you look at the difference between f of x sub 0 plus h and f of x sub 0, then that's this distance here. Of course, that's h. the difference in the x coordinates is h. And when when we don't take the limit, this gives the slope of the second line here, joining points P and Q. However, when you take the limit, as h goes to 0, you move this point towards P, and at the end you get this tangent line. So that's the basic idea. Okay, so when you don't take the limit, you get the slope of the second line, and as you move Q towards P, as h goes to 0, that's the same thing, you get the slope of the tangent line. Actually, we have mentioned this when we are studying chapter 2. Okay, let's give a specific example now. Let y is equal to 1 over x. And let's find the tangent line at point A and 1 over a. So x is a, y is 1 over a. And let's ask this question. Is there a tangent line with slope minus 1 over 4? Okay, now let's calculate f of x of 0 plus h minus f of x of 0 divided by h, and then take the limit. Okay, so it's 1 over a plus h minus 1 over a, all divided by h. Of course, if you do this subtraction, you get minus h. Because if you equate the denominators here, a is here, a plus h is here. So a's cancel out, you get minus h here. And now in the denominator, you have a and a plus h and plus another h. The h's cancel out, and as h goes to 0, you get minus 1 over a squared. So the slope of this tangent line at this point for this function is minus 1 over a squared. So we can answer this question, is there a tangent line with slope minus 1 over 4? Yeah, there's a tangent line with slope minus 1 over 4 at a is equal to 2 and at a is equal to minus 2. So we can write the equation of the tangent line using point slope formula for the line. So 1 over a is the y sub 0. So minus 1 over a squared times x minus a is the equation of the tangent line. Or you can shortly write this as minus 1 over a squared times x plus 2 over a, because if you open this up. Now at a is equal to 2, slope is minus 1 over 4, and the tangent line is minus 1 over 4x plus 1. Because when a is equal to 2, it cancels with this when you open it up. So it's plus, so you get 2 over a, and the 2 over 2 is equal to 1. Now, also at a is equal to minus 2, you have the same slope. It's minus 1 over 4 again. So in this case, however, the equation of the tangent line changes because the y-intercept changes, and it becomes minus 1 over 4x minus 1. Because in this case, if you put a is equal to minus 2, that's x plus 2. That's minus 1 over 2. So there is another minus. It's minus 1 over 2 plus minus 1 over 2. It makes minus 1. So that's how you find the slope of the tangent line, and which is also the slope of the curve. It's called the slope of the curve, which is also the slope of the tangent line. Let's continue and see this in the figure. Here you have y is equal to 1 over x, and the slope is minus 1 over 4 here. But when you put x is equal to minus 1, the slope is minus 1 at this point. That's point minus 1. or we can just show that y is equal to 1 over x here. So the slope is minus 1 over 4 at x equal to 2, and x equal to minus 2, as we have shown algebraically. This is just a pictorial representation of this situation. Now we have come to the definition of the derivative. The derivative of a function f at a certain point x of 0 is denoted by f prime of x of 0. That means the first derivative. And it's this limit. So it's the same thing, actually. Again, you calculate f of x of 0 plus h minus f of x of 0 divided by h, and take the limit as h goes to 0 from both sides. Now, if this limit exists, then you say that derivative of a function at x of 0 is whatever the value you get here after taking the limit. So the derivative of a function, slope of the tangent line, or slope of the curve, given curve at a certain point, are the same thing. Let's now continue. Actually, this limit that we have defined has all these four interpretations: the slope of the graph at x equal to x of 0, the slope of the tangent line at x equal to x of 0, and of course the rate of changes of f of x at x of 0. Actually, this is instantaneous rate of change. If h is not 0, that's the average rate of change. But when you take the limit as h goes to 0, you get instantaneous rate of change of the function at x equal to 0. And it's equal to the derivative of f at x equal to 0. All these things are the same. Now we can consider derivative as a function, because when you take the derivative of the curve that you have, y is equal to f of x, you get f prime of x. So you take the derivative at every point in an open interval. So the derivative of the function f of x with respect to the variable x is the function f prime, whose value at x is this. So when you want to find the derivative as a function, you calculate this limit as h goes to 0. When you want to find the derivative at a certain point x of 0, instead of f x plus h, you have x of 0 plus h, and this is f of x of 0. So we can consider the derivative as another function which we obtain by taking this limit on an open interval. There is another equivalent definition of the derivative at a certain point, or derivative as a function. You have same here, you put h is equal to z minus x. So this is f of z minus f of x. And then you take the limit as z goes to x of f of z minus f of x, z minus x. That's the same thing. Instead of z, you can put here x plus h also. And you change this as h and take the limit as h goes to 0. But you can calculate the derivative with this expression also. And you take the limit of this expression as z goes to x. Sorry. Okay, so alternative formula for the derivative is given like this. You should bear this in mind. When you calculate the derivatives of certain function, you might need this formula, and we will see that later on. Okay, let's look at an example. You have y is equal to square root of x, and you want to find the slope of the tangent line at 0.42, because when x is equal to 4, y is equal to 2. Now you can use this formula that we have shown before, f of z minus f of x divided by z minus x. That's equal to, since x is square root, so square root of z minus square root of x divided by z minus x. Now I can factorize z minus x, because z minus x is equal to square root of z minus square root of x, square root of z plus square root of x. When you multiply these two, you get z minus x. But right now these cancel out as z approaches x, and so you have 1 over 2 square root x as the derivative of the function y is equal to x. So you can evaluate this at 0.42. When you put x4 here, that's result is 2. So that's 1 over 4 is the slope of the tangent line, or slope of the curve at 0.42, as you can see here. So you can use both formulation to calculate the derivative. We are going to calculate some derivatives later on, and we will use both approaches. Now that's the definition. A function f of x is called differentiable on an open interval if the limit, that's f of x plus h minus f of x divided by h, and the limit h goes to 0, exists for every x in this interval. So we have to be sure that the derivative, this limit, exists for every point x in this interval. And we say f of x is differentiable in the open interval. Now, if you want to look at the closed interval, so we say a function f of x is called differentiable on a closed interval, a, b, if the limit, this limit exists at all interior points in the interval. Now, at the end points, we cannot take a two-sided limit. For instance, at a, you have to calculate h goes to 0 from the right-hand side, because on the left of a, the function is not defined. Now, for b, you have to take the limit as h goes to 0 from the left-hand side, because on the right-hand side of b, the function is not defined. And so we call these right-hand derivative, this one at point A, and its left-hand derivative at point B. So at the endpoints, you just say that you have one-sided limit, so you give a name right-hand derivative as you approach 0 from the right-hand side, and left-hand derivative as you approach 0 from the left-hand side. So this is sort of similar to the continuity. If you recall in chapter 2, we said that a function is continuous on a closed interval, okay? If the limit at the interior points is the value of the function at points, and however at the end points, we look at right-hand and left-hand limits. So it's similar to the notion of continuity. So you have here, instead of left-right continuity, you have left-hand, right-hand derivatives. Let's continue. That's a function given. When you draw the slopes of this function, for instance, at A, at B, at C, D, and E, you can sort of join the slopes and get the derivative of a function. That's f of x. At A, the slope is 0, so that's what we have here, 0. At B, the slope is negative, and that's what we have. C is the same thing. At D, is the slope 0, so we cross the x-axis, and E, slope is positive. So by joining the values here, because we have slope 0, slope -1, slope -4/3, slope 0 again, and slope 8 here again. So joining these points, we have a rough sketch of the derivative of the function. What type of function is the derivative we see from here? Okay, that shows the right hand and the left hand derivatives for the closed interval. As you know, at A, because it's the left endpoint, the function is defined between A and B. You have a right hand derivative, which is this red line. Okay, so that's the tangent to A at this point. But the limit exists, only right-hand limit exists. So we call this right-hand derivatives. And at B, you have the left-hand derivative, and that's the tangent line, red. These are second lines, actually. What you basically do is that's black is the second line, and you take these points towards here, and you get the tangent line here. The same is here also. Okay, so that's a pictorial representation of the differentiability. But all the interior points, as you know, there are no gaps and no holes in this curve. The function is differentiable at all interior points, and at the endpoints, the function has right and left hand derivative, and that's what we conclude. Okay, let's look at the typical examples. Y is equal to absolute value of x, and we want to find out the derivative at 0. So f of 0 plus h minus f of 0, okay, that's 0 plus h absolute value because you're approaching from the right-hand side. So that's h over h, which is equal to 1. So the derivative at 0 when you approach from the right-hand side is 1. Now let's look at the derivative when you approach from the left-hand side. So f of 0 plus h and 0 plus h here. But now h is negative here because you approach 0 from the left-hand side. This is absolute value, this is positive, but that's negative. So you have minus h over h, that's minus 1. So you have two different slopes, and so that's not a two-sided. So we say that this function is not differentiable at point 0. It's differentiable elsewhere for all the interior points, and that's an interior point too of this function, but it's not differentiable, although it is continuous at this point, because the limit when you approach from the right and left are the same, and it's equal to the value of the function. It's continuous but not differentiable at this point. Now let's look at this function, y is equal to square root of x. Now this function is not defined for negative values of x. So it's only defined for positive values. what happens to the, if I take the derivative of this function at 0? So f of 0 plus h minus f of 0 divided by h, that's the square root of 0 plus h, and that's h minus 0. So square root of h cancels out with h here, so you have 1 over h, which goes to infinity as you approach 0 from the right-hand side. You cannot approach from the left-hand side, so you only approach from the right-hand side. So that's infinity. So we say that this function at 0 has a vertical tangent because the slope of the tangent line is infinity. So this function has a vertical tangent. Okay, in certain cases, this was the previous two examples was about non-differentiability in a way. The function is not differentiable at some points, but let's sort of classify it. A cusp is a sharp point, actually, and when you have in the graph of a function a sharp point, then at this point the function is not differentiable. Let's give an example. Y is equal to x squared between 0 and 1. When x is between 0 and 1, in a closed interval, it's x squared. But it's x minus 2 squared between 1 and infinity. Now, so we are going to approach, we want to calculate the derivative at x equal to 1. So if you approach from the left to 1, this function is valid. So that's f of 1 plus h minus f of 1 divided h. Then you want to find the left-hand limit. Now, if you open this up, 1 plus 2h plus h squared. So once f of 1 is 1, so once cancel out, you have 2h plus h squared divided by h. Now, if you cancel out the h here, and take the limit as x, h goes to 0 from the left-hand side, the result is 2. So the derivative, left-hand derivative, the left-hand derivative is 2 at point 1. Now you take the, as h goes to 0 from the right-hand side of f of 1 plus h minus f of 1 divided by h. Now on this side, this function is effective when you approach from the right. So f of 1 plus h is equal to 1 plus h minus 2 squared. Okay, so if you open this up, again, ones cancel out, you have h minus 2 square term. So that's minus 2h plus h squared. Now, when you cancel out h and take as h, so right-hand and left-hand limits are not, so it does not have an ordinary limit at this point. So this function is not differentiable at this point at x equal to 1. Second is a corner. A corner, you know what a corner is. It could be a 90 degrees right angle between the two walls. So you have y is equal to x squared again at 0, x1. But afterwards, y is equal to 1 over x between 1 and infinity. Okay? So actually, these functions, this function is not differentiable, but it's continuous at this point because these have the same values at 1. Okay? Same is here. this is a continuous function at point 1. But let's look at the limits. So from the left-hand side, we know, but let's write it again. So from the left-hand side, the limit is 2. Let's try to calculate the limit from the right-hand side. Here is the function 1 over x. So f of 1 plus h is 1 over 1 plus h minus 1. F of 1 is 1. So I take the limit as h approaches to 0 from the right-hand side. Now, if you equate the denominators, what you have here, minus h, and h times 1 plus h here down in the denominator. H's cancel out, you have minus 1. So again, right-hand derivative and left-hand derivatives are not equal, so the function is not differentiable at x equal to 1. It's a vertical tangent, but this is not a vertical tangent, so you can forget about this terminology here. But y is equal to 1 over x. The derivative is what? Minus 1 over x squared. We are going to prove this later on, that this is true. And so that's not differentiable here at x equal to 0. So you can have functions which are not differentiable at certain points. Here is a pictorial representation of the cusp. So on this side, on the left-hand side, if you move point Q towards P, you know the second line here. Here in this case, the tangent line goes to infinity. And if you approach from the right-hand side, that goes to minus infinity. So that's a cusp. That's an example of a cusp. Now that's the actual vertical tangent here. You have a function which is continuous all out. There are no holes and no gaps in the function. So if you take the second lines towards P, you get a vertical tangent, which means the limit is infinity. Actually, the limit does not exist, but we still call it a vertical tangent. That's a typical example of it. Another typical example we have seen, the square root of x. Its derivative is infinity at 0, so it has a vertical tangent. And that's the representation of a corner. Okay, so you can, this is sort of x squared. That's some other function. But as you can see, these derivatives are not equal. The limits are not equal. So these are the pictorial representations of the points where now jump discontinuity is also important, and that's a pictorial representation of jump discontinuity. And you have x squared and 1 over x between 0 and 2. So you look at the limit f of x plus h minus f of x at x equal to 2. From the left-hand side, that's x squared, so you have this term. And you get, when you open this up, that's 4 plus 4h plus h squared. 4's cancel out, and h, one of the h's cancel out here. You are left with 4 plus h. When you take the limit as h goes to 0, you are left with 4. And here, when you approach from the right-hand side, that's the function 4 to 2. So that's 1 over 2 plus h minus 1 over 2, because at x equal to 2, 1 over x is 1 over 2. And if you equate the denominator, you have minus h divided by 2h plus 2 plus h. So h's cancel out, you have minus 1 more. And so a jump, if you have a jump discontinuity, you don't have differentiability. That's another. There's no jump, but the function value is not defined here. As you can see, there is a gap. This function, that's not in the domain of the function, so you don't have differentiability. That's another. The third example is wild oscillation, because it's x times sine 1 over x. Okay, when x is not 0, it's 0 there. So because of the wild oscillation, you don't have a limit, so not a derivative also. As you can see, derivatives are based on limits. Okay, now there is an important result here. Differentiability implies continuity. If f has a derivative at x equal to c, then f is continuous at x equal to c. So the converse is not true, of course. If the function is differentiable, it must be continuous at a certain point. But if it's continuous, it is differentiable is not true, as we have seen examples previously. So the function may be continuous, but not differentiable at that point. But if it's differentiable at a point, the function is continuous. Let's prove that. Okay, we have to show that this limit exists as x approaches c. We are looking at a certain point, and the limit must be equal to the value of the function. That's the definition of continuity. So let's look at f of c plus h. I can write this as follows. Add f of c, subtract f of c, so that's the same thing. And now this term I can write it like this, f of c plus h minus f of c divided by h and multiply h. So f of c plus h, this is like the derivative of the function, but that's multiplied with h. Now as x approaches c, from both hand sides, is that f of c plus h, the limit of f of c plus h approaches to 0 from both sides. And then this is approaches to 0. Now f of c is constant. Since the function is differentiable, we have this limit multiplied by h. Okay, this is some number. The limit exists because we assume that the function is differentiable. So we have f of c at the end plus the limit as h goes to 0, f prime of c times h. So I know that there is some real number here, prime of c, since the function is differentiable, but h goes to 0, that goes to 0. So that's the proof that the function is continuous, because that's equal to f of c. So the limit exists as x approaches to c, and it's equal to the value of the function at c. So that's the proof that if a function is differentiable at a certain point, it must be continuous. But the converse is not true. If it is differentiable, it does not. It is continuous. But if it is continuous, it is not necessarily differentiable. Okay, as we have seen a lot of examples. Okay, let's look at the differentiation rules then. These are similar to the rules for limits. Okay, because derivative is based on derivative of a constant function. What's the derivative of a constant function? Obviously, it is 0, because f of x of 0 plus h minus f of x of 0 is always the same. That's 0. So the derivative of the function constant function is 0. And pictorially we can see here that's x. The function has value c at x, and it again has value c at x plus h. So f of x plus h minus f of x is always 0. So the derivative of the constant function is always 0. Now, derivative of a positive integer power, x to the n is an integer and positive integer, is equal to n times x to the n minus 1. So you multiply by n and take the power n minus 1. Okay, that's f prime of x, f of z minus f of x divided by z minus x. So f of z is z to the n, f of x is x to the n, and z minus x. Now you can factorize the numerator polynomial as this: z minus x times x to the n minus 1, x to the n minus 2x, sorry, z to the n minus 1, z to the n minus 2 times x, z to the n minus 3 times x squared, and goes on like this until you are at x equal to the n to the minus 1. So it is always possible to factorize this type of expressions, z minus x. You can always take it out. But if you take the limit as z goes to x, what we have? Now this term goes to 0, but it cancels out with this one. That goes to 0. So we are left with this expression. Now as z goes to x, that's x to the n minus 1. That's also x to the n minus 1, because z to the n minus 2 times x, that's x to the n minus 1 if z goes to x. Same all these here. How many terms here? There are n terms here. So that's n times x to the n minus 1. So that's the proof of the fact that if you have a positive integer power and you take the derivative, it's equal to n times x to the n minus n. Later on, we are going to prove that this is also true for negative powers, and actually it's true for all real numbers, but that we'll show later. So if you look at some of the examples here, if you take the derivative of 1, which is a constant value, the derivative is 0. If you take the derivative of x, which is equal to 1. If you take the derivative of x squared 2 times x to the 2 minus 1, that's 2x. Who's playing with the pen? Stop it. If it's x cubed, 3x squared. x4, that's 4x cubed. And you can go on like this. So, there's an alternative proof. You can try this at home. But what you do is you use this formula, that's x plus h to the power n minus x to the n. Okay, so you can open this up as follows. This notation, n over 1, which means n factorial divided by 1 factorial and n minus 1 factorial. Okay, that's the same thing also, and that's the same thing. Okay, divided by h. That's a binomial expansion of this term. At the end, you have to, of course, x to the n as the minus term, but the first term binomial expansion is this. Actually, what this means that's x to the n, okay, that's n times h x to the n minus 1. That's n over n times n minus 1 times h squared x to the n minus 2. And it goes on like this. Now, the h's here cancel out, but there's h squared, it still remains. All these terms as h goes to 0 is 0. Okay? So you only have x to the n's cancel out with this one. You only have this term, which is n times, because h is canceled here, it's n times x to the n minus 1. So that's the derivative. Now, the general version of this power rule, if n is any real number, then we have the same thing. But we did not prove it yet. We are going to prove it, but we did not prove it yet. Okay, let's continue. Derivative constant multiple rule. Now, if you multiply a function with a constant, how do you take the derivative? It says here you can take the constant out. Let's prove it. F prime of x, that's the derivative. C times u x plus h, c times ux. Now, since you are taking the limit and c is constant here and common, you can just take it out. You look at this one, which is the derivative of u of x, of this u prime of x times c. Since the limit law says that the constant you can take out and take the limit of the remaining. Let's continue with another function. This is sort of a pictorial representation of the constant multiple rule. So you have y is equal to x squared. The slope at 0.11 is 2. Now, when you multiply this by 3, so this point here, that's another thing, you know that it's stretched along y-axis. So the slope at 1,3 is just 6, triples the slope. So slope is actually the derivative in a sense at a certain point. So when you have a constant multiplying a function, actually you're multiplying its derivative with a constant, the same constant. Okay, let's look at sum rule. If you have the sum of two functions, u and v, which are both functions of x, then the derivative is the derivative of u plus derivative v. It's easy to see it here. When you have a sum of two functions, that's ux at x plus h and vx plus h. Here you have u of x plus v of x on the negative side. So you can just rearrange these terms. You have here this and this. So h divides both of them. When you take the limit, what you actually get, this is the derivative of u, and this is the derivative of v. That's simple to see. Okay, so when you take the difference, you have the same thing actually, because the derivative of a difference is the x of u plus minus v. Okay, so since when you add, you take the constant out, you take this constant out, which is minus 1 on v. That's what you get. So that's the same thing. Okay, let's give a break at this point for 10 minutes. We will convene at 10 o'clock.